Okay, so the problem for this week is the week 8 quadrature, yeah? So first you have to write a program to compute this table. Okay, so first we have to download Simpson.m, okay, to compute the Simpson rules with step size h. Okay, and then we will use that to compute these integrals approximately with a different step size. Okay, and then we print out this table. So this table, so every row has 4 numbers, yeah. So except row 1 and row 2, you don't have any last number. So the first one is the number of subintervals, okay, and the second number is the width of the subintervals, and the third number is just the approximation of the integrals using Simpson rules, and the last one is the order of convergence row. So row is given by this formula. Okay, so we will discuss about this later. So the first step is you have to download Simpson.m. So you go to the website, you go to Moodle, and you click on Labs week 8, and you see Simpson.m here. Okay, so now I will show what Simpson.m looks like. Okay, so I will open my MATLAB. So now let me share my MATLAB. So now if you see my MATLAB screen, you will see Simpson .m here. Okay, so let's discuss a little bit about Simpson.m. So first, okay, so remember that we have we have the formula for one interval. So for one interval, for one subinterval, yeah, say from A to B, then what is the midpoint rules? So the midpoint rules is just the value of the function at the midpoint. So A plus B over 2. Okay, so you take the value of the function at that midpoint and you multiply by the width of the intervals. So B minus A, yeah. So then what is the trapezoidal rules? So trapezoidal rules over that intervals is just the average of FA plus FB divided by 2, yeah. And then you multiply with the width of, so maybe I just say that 0.5 here. You multiply with the width of the intervals, yeah. So and then what is the Simpson rules? So Simpson rules, remember Simpson rules is over the intervals A, B, it just B minus A over 6. Okay, multiplies with the value at the left plus 4 times the value at the midpoints, yeah. Multiply, and plus the value at the right hand side. Okay. So now you see that there is there is the relation. So if I take 2m/3, so if I take 2m/3, then what do I have? So I just have exactly this one, yeah. Multiply by 2/3, so 2/3, yeah. So multiply by 2/3. Okay. And if I plus, so if I take t divided by 3, so t divided by 3, then what is the value now? So now it will be t here, you divide it by 3, so this one will be 1/6. Okay. And if you add it up, so if you add it up, so 2m/3 plus t/3. So you see that gives you, so if I take b minus a/6 to be the common factor, okay, then what do I have? Then I have f of a plus f of b, yeah. So this one will be the terms come from t/3, and then for 2m/3. So now because you divide it by 6, you got 4 times f of the midpoint. Okay, so this is exactly Simpson rules. So that then we have this relation. So that is exactly this relation. So the Simpson rules is just 2/3 of the midpoint plus the trapezoidal rules. Yeah. So now that is the explanation of the last line. So now how about the first few lines? Okay, so now this one, remember this is the formula when you have only one subintervals. Okay, so now if I have n subintervals, yeah, so more general, suppose I have x equal a partition. So now x is a vector. X is a vector, yeah. So x1, x2, well, maybe write in terms of MATLAB notation, yeah. x3 dot up to the last one is say xn. Okay. Then what is the half? So this command h, yeah. So this command h diff of x. Okay, so there is no symbolic here. So if a symbolic package, then diff could mean the derivative, but here it's just a difference. So the h here, okay, this command diff, if you look it up, it just compute the difference between the adjacent values. So the first entries will be x2 minus x1, and the second entries will be x3 minus x2, and so on. You know, up to the last one is xn minus 1. Yeah. So h just gives you the width of the subintervals. Okay. So what is x half? So x half is exactly the midpoint. So if you take x1, okay, so if you take x1 plus h/2, okay, then essentially it's just a midpoint, yeah. So x2 plus h/2. So this one actually should be the very first element of h, so h1. Okay, so this one is h2, and so on. So this one gives you exactly the midpoints, yeah. plus, so this one is xn minus 1 plus hn over 2, yeah? So it gives you exactly the midpoint. So now what is the area of the rectangles, yeah? So the area of the rectangles will be f of x1 plus h1 over 2 times h, right? Maybe h1, yeah? And then plus f of, so the midpoint here, so the midpoint will be, so the midpoint here, so f of x2 plus h2 over 2 times h, and so on. So you add to the last one. So f of xn minus 1 plus hn over 2. Right? So this one, you see this command sum, right? Then h here, so you take every h here, right? Well, actually, I mean, this one is multiply element wise, but you see, then this one just means h1, and then plus f at midpoint h2. So this one should be h2, and so on. So this one gives you the midpoints over on the subintervals, yeah. And similarly, you have the trapezoidal rule. So the trapezoidal rules is, you know, I mean, you take 0.5, yeah, of f of x1 plus f of x2, right? And then multiply by h1. And you add the second one, the second trapezium, the second area is f of x2 plus f of x3 multiplied by 0.5 multiplies by h2, and so on. And you see that exactly this sum, yeah? So exactly this sum. So x from 1 to n minus 1, this means that x1, x2 up to xn minus 1, yeah? And then you see, then you have x2, okay, plus x3, you know, up to xn. So exactly implement these ones. And then after that, you just implement the Simpson rules, okay? So this one is true for one subintervals, then it's true for n subintervals as well, because the sum, you know, is linear. So the sum is linear, so you can add it up. So that is why Simpson, you know, how it works, yeah? So any question about this Simpson.m? So how do we use it? Okay, so now how do we use it? So now how do we use Simpson.m? How to use Simpson.m? How to use the function? Okay. So now give me a function you want to integrate. So give me a function. So anyone give me a function? Any function that you want to integrate, and the intervals as well. Yeah, but this one, you see, I want some simple function so that we can check the exact integrals. So this one you don't, yeah, okay, x squared, yeah. So x squared is a good function. At least we want to check whether it works or not, yeah. So x squared, and you want to integral from where to where? One to 5. That's good. So the left is 1 and the right hand side is 5, yeah. So now I will go on the function Simpson. So S M T. So S for Simpson, M for middle, and T for trapezoidals, yeah. So I got it Simpson and F. Well, now we have to construct a partition. So first, have to construct partition. Okay, so now you can construct a equally spaced partition. So let H equal, say, 10 to the minus 2. Yeah. Then you define a partition X to be, so the X here is a dummy variable, so you can reuse it. Yeah. So X here is from A increased by H and then ends at B. Okay, so this is how you construct a partition. Yeah. And now you put it in. So this is Simpson. Yeah. So then you print out the results. So S equal whatever it is, midpoint rules give you whatever it is, and trapezoidal rules give you whatever it is. Yeah. And S empty. Okay. So now let me run it. So, well, we have to write down the name for this. So say test Simpson. So test Simpson. Okay. So you can see that the Simpson give you 41 and 1/3. Okay, 41 and so now what is the exact integrals? So if you take the exact integrals, yeah, so the exact integrals will be, exact integral is x cubed over 3, yeah, and you evaluate from 1 to 5, right? So what is 1/3, yeah, and then you have, say this one should be 1 to 5, yeah, and you should have 5/3 minus 1, yeah. So what is 1? So 5 to the 3rd minus 1, so 124. So 124 divided by 3. Okay, so 124 divided by 3 should be, so 124 divided by 3, yeah, should be 41 and 1/3. Okay, so you see the Simpson rule seems to give you the most accurate. Okay, because this one, it has 3 up to, you know, you can write out more digits, yeah, so maybe say 9 digits, yeah. And you run it again, so you see that Simpson rules give you up to 9 digits of the solution, and midpoint rules give you only 4 digits, yeah. Trapezoidal rules about 4 digits as well. So Simpson rule is more accurate, because remember Simpson rules is you approximate the area under a parabola. Okay, and an x square is a parabola, so it become exact. Actually, it become exact. Yeah. Okay. So the Simpson rules, it's just a parabola, right? The area under the parabola. So now, how do I use this to write out the solution for my problem? So now go back to the question, yeah. So now I want to show you the question again. So now we know how to we know how to use Simpson's function, yeah. So how do we compute this table? So first, you know, like what is the relation between n and h here? And what is the pattern for n? So how do you write down this table? So suppose you want to program it, yeah? So how do you write down this table? Yes, 2 to the k, right? Because it is, because n is this one already. So n is 2 to the k, yeah? So k is 2, 3, 4, 5, 6, 7, yeah? Okay, so then n is just 2 to the k. So now we say that, okay, now for k equal 2 to 7, yeah? So we go back here. And I say that, okay, so for k equal 2 to 7, yeah? Then n is 2 to the k, okay? Well, but first, remember we have to define our function first, yeah? Because otherwise we cannot use Simpson with our an integrand. So remember the function f is just given by 2 over, sorry, 1 over 2 plus logarithm x. So remember in MATLAB, logarithm here is a natural log, okay? So logarithm here is a natural log, so it's ln, yeah? And we have to give the left-hand side, so the left-hand side is a equal 1, b equal 2. So the integral is from 1 to 2, right? Okay, so now what is the width of the subintervals? And what is the partition? So the partition is x is a h to b, yeah? And now if, what is the width? Yeah, so the width is 1 over n, is correct, yeah? So you can see that from the table. So the width is just 1 over n. And now remember we call Simpson again. So SMT equals Simpson f and x, okay? And now we have to print out the table. So now we have to print out the table. So now go back to the question. You can see that the table has, maybe let me cut and paste the table, yeah? So I cut and paste the table into my program. So the table look like this, yeah? So this is what I want to print out, yeah? So now, you can write down before you start the for loops, yeah? So you can print out n h s h and row h. So we just write down the first line of the table, so the title line, yeah? So now we print out what? So we have to print out. So now suppose we will not discuss row, yeah? So we will discuss row after we print out the table. So let's see, make row equal 1. Okay, so now I will print out n as a decimal. So how many space for the decimal? So 3 spaces for the decimal. And I print out h. So h will be a floating point. So %f. So 1 digit before the dot. And how many digits after the dot? So 6 digits after the dots for h. Yeah, and then s of h. So this is s of h, yeah. And this is row. So we can Okay, so now how many digits for S of H? So we have 1 digits before the dot, and how many digits after the dot? 3, 6, 12, 15, 18, yeah? So 18 digits after the dot. And then how many? So 1 here, 4 digits here. And I print out N, H, S, and row. Okay, so let me run it. So I run it, so I have to save. So the question asks you to save in a row table. Okay, so I click run, and what do I see? So there's something wrong here. So N, N here, H here, S here, row here. 1, 2, 3, 4, 1, 2, 3, 4. Something is, then I missed the F here, okay? Okay, so you can see that. So I print out exactly the table. I set the last one. I think we print out a bit more digits than needed. But it's okay, it's not very important, yeah. So now how do we compute row? So row, so N has to be a bit like this. Okay, so so it's not a big problem. Okay, but now you see it, right? So now you see how I compute the tables, yeah. So now how do I compute row? So we have the function already, yeah. So now go back to the problem. So how do I compute row? So if I go back to the problem, so now how do I compute row? So row is given by this formula, yeah. So where do I find S for H, S to H, and SH? So how do I compute row? So you see the problem, yeah. So I mean I put in H already. I put in Simpson to compute S of H, right? So now how do I compute row? By this formula. Anyone? So in the lab, you're supposed to do it, you know, like on your computer, you know, in your computer, because you need to practice. Otherwise, I mean, if you just watch me doing it, then you will not learn anything. So now how do I compute row? Well, first you look at this one. So suppose H is this, then what is 2H? Well, 2H is 0.5, right? So 0.5 is outside the table, yeah? So we cannot start here. So now suppose I have H equal this. Yeah, 0.125. Then what is S to H? Well, SH is here, yeah. Then 2H is 0.25, so it's okay. So this one is S to H. But what is S for H? So for H will be, so 1/2, okay, so outside the table. Okay, so now I have to start from here. So if H is here, so if H is 1/16, yeah, then this is my 2H, and this one is 4H, yeah. So this one will be SH, S2H, and S4H. So every time you want to compute a row H, then you need the results from 3 consecutive rows in the table. Okay. So how do we do it? Anyone? Yeah, but what is your SH1? Okay, so right now, so you see now you say that maybe we should save it, right? Because when you put an index like this, yeah, then you have to give, this one is like a vector, right? So SH is a vector, yeah. Then, you know, I mean, okay, so first we have to give a vectors, yeah, to save all the values, yeah. So let we go back to the program, yeah. So now I will make a new vectors called SH. Okay. So how many elements in SH? How many elements? Well, so it's like a row vectors, yeah, or a column vectors, but how many elements? Yeah, so SH is the results, but you want to save it, yeah? So you want to save it. So you want, essentially you want to save all the results in the table. So 1, 2, 3, 4, 5, 6. So you want to save all the 6 values. Yeah, so you save all the rows, okay? And then every time you compute from the Simpson, then you save it. So HH here, you know, K equal S, yeah? But because K start from 2, okay? And SH can start from 1. So we should put, say, K minus 1 here. Okay, so now I save the results. So now if I run it, then you will see that my SH contain all the results here. You see in my command window, so SH contains all the numbers, yeah, in the, from row 1 to row 6, yeah. And now, okay, so now how do I compute this row? So, well, see, row doesn't make any sense if you have K, you know, equal 2 or 3, yeah. Because K equal 2 or 3, you have nothing, you know, to compute. So K has to be bigger than 3. Yeah. So otherwise, I just do not print out row. Okay, so now tell me the formula for computing row. So this one is when we cannot compute row, yeah. So row. So row is not available for the the first two rows. Yeah. Okay, so now give me the formula for, so your formula now is correct, but only for the special case when k equal 3. Okay, so I can copy this. Okay, I can copy this, but it's only correct for k equal 3. Yeah, so this one is actually for k equal 4, right? So this one is only for k equal 4. So this one is only for k equal 4, yeah. So and you need the logarithm of this, logarithm of the whole thing here divided by logarithm of 2. So what is the general case? So you got the correct formula for particular case already for k equal 4, yeah. So what is the correct? What is the formula for general k? Okay, so let me copy in your formula and see whether it works. Yeah. Oh, sorry, I copied the wrong formula. Yeah, so you got the correct formula. Yeah, so let's see. Okay, so I just cut and paste your formula in. Yeah, so now, so make sure that we have enough open and close parentheses. Yeah. Okay, so let's run it again. Yeah, so we run it again. 14. So this line. Yeah, so this line. So we got SH k minus 2 k minus 1. You see, in order to avoid that syntax errors, so maybe we say that S H equal S already, so we don't have to worry. So S to H, okay, is nothing but S. Well, S to H is just SK minus 2, right? Yeah. Okay, because this is a current one, so this one is SH. Yeah. Okay, so this one will be your S to H. Okay, the previous one. So S for H will be the one before the previous one. So okay, and now if I use the formula, then this will be S for H minus S to H. Okay, so now let's look at the formula. Yeah. No. S to H is not the second element, but the elements just before it. You know, this is the current element. So SH is the current element. So S to H is just the previous element. So remember the table. If you look at the table, go back to the table. You see, look at the table, yeah? So suppose H is 1/16, okay? Then 2H is just right before it, okay? And 4H is just 2 rows on top of it. So you see, if you start from here, so this is H here, then 2H is the previous row, and 4H is 2 rows, you know, before that. Yeah. So because the table designed that, you know, you go down, I mean, you multiply n by 2, right? So it's meant that H going down by a factor of 2. every row. Yeah. So now I'm doing I'm doing it. Yeah. So now so S2H is the row before that. Yeah. So the row just before that, and this one is 2 rows before the current rows. Yeah. Okay. So now if I put in the formula, so now the formula will be S4H minus S2H divided by SH minus S. So now I'm going back to my MATLAB again. Yeah. Okay. So this one is S4H is K minus 3. Okay. Because the current is K minus 1. So S2H is K minus 2. Yeah. Because the current is K minus 1. Yeah. And so now this one is S2H, okay, minus SH, and SH is just S because we stay in here, yeah. And you see when we write out like this, then we see that we miss one parenthesis, yeah. So it helps you to track the parenthesis, yeah. So now if you run it again, so now you got the table correctly. So 3.9 something, yeah. Okay, so we got exactly this table. So you see the tricky part is just how to compute the row. You know, other part I just from the way you compute Simpson, yeah. And so this one related to the theory, because if you look back at the question, okay, we discussed the theory maybe tomorrow in the lectures, yeah. But if you look at the question here, so the row here, okay, it's just the order of the errors, yeah, because if you take the exact integral I minus SH, then this is the errors of the quadrature of the Simpson rules, and the errors is of the order H to the row, and row is, you know, we can show in the tutorial, you know, maybe next week, yeah, that can be computed by this. You see, so the good thing is you don't need to know the exact integrals I, but you still try to find out what is the order of conversion row, okay, based on this trick, yeah. And you see in this table, I mean, from this table, you can derive what is the constant C as well. So by this formula, so you can do the same. And if I use exactly the same loops, I can compute the constant C, yeah. So if I go back to my MATLAB script, okay, so now I want to compute the table. So let me copy the table first, yeah. So now I want the second table. So the second table look like this. Okay, so you print out N and H. Okay, but now you don't have to, well, you still need to compute S of H, yeah. But now you need to compute C of H. So now how do we do that? Well, maybe let me make another script, yeah. Maybe I call it, so maybe C table. So I copy and paste the whole thing here. I don't need the first table. I just need the second table. Okay. So So for the second table, so if you look at the question, then you need only SH and S2H. So HH and S2H. So the formula, we don't need S for H anymore. So now what we need is, we don't need this anymore, yeah. And then we don't need this row anymore, yeah. So now if you don't need the S for H, then K can be bigger than 2, right? So you need to compute only this S2H, yeah. So now if you look back at the formula, then it will be SH minus S2H. So SH minus S2H, right? Because, and then divided by 15H4. 15 times H to the 4, yeah. And you need to print out only H and C of H. So C of H is, it just print out as a scientific one, yeah. So NH, C of H. And else you don't have to worry, yeah. So CH is not available. So CH is not, well, I think we don't have to print out anything. So because N start from 4, so we don't have to print out the one before that. Okay, so and now we run it. So we run it. Okay, so maybe this one C table. So see, we got exactly the same, see? So N equal 8, H is 0.125, and CH. So this one is just CH. And that's it. Okay, so you got exactly the same table. Okay. So now the last question is very similar. So you just replace the function by sine of square root x from 0 to 1 and see what happened. Okay, so sine of square root x, so we can cut and paste and replace the function. So now I'm going to cut and paste this one, yeah, into a new one. So we call it, we remove this one, yeah. And now we just replace the function by sine of square root of x from 0 to 1. Okay, and you run it again. So now we run it. So we save at math.row.m. Okay, so what do you see? So what is the value of rho here? So what is the value of rho? And why is that? So rho is only 1.5. So before you got up to 3.9 or close to 0, yeah? And now it just give you only 1.5. So what is going on? Okay. And so now the next question say that, okay, so what happens if you make a substitution? Okay, so you do exactly the same, but now you make a substitution. Yeah, so this is the same integral, yeah, but if you make t equals square root x, okay, or t squared equal x, then you transform it into 2t sine t. Then what do you see? So 2t sine t. So if I make f is to t sine t, yeah. Okay, and then what do I see? So I run it again. So now you see that it go back to 4, yeah. So what is going on here? So why is that? So why do we see that? You know, I mean, if you see the square root, then I mean it just dropped down to 1.5, and I made a chain of variables, and then it backs to 4.0 again. So why is that the case? So anyone, did you read the theory yet, or maybe we should discuss it tomorrow? Yeah. So you see, before we have a square root of x here, and the order dropped down to 1.5. Yeah. But you made a change of variables, so the same integrals, and it back up again. Okay. So the order, the higher the order, the faster the error is going down, right? So that means that you haven't read the lecture notes, yeah. So maybe we discuss that tomorrow, yeah. So that is the end of the lab today.